Hey everyone, today we're going to be learning about a force that we are all very familiar with, friction. It is a part of our everyday lives and almost every single thing that we do, even just walking through air has some type of friction, and we expend energy from our body just to try and walk through the air, even though it is very small. Um, and that is friction. It is a vector quantity. It is a force that opposes relative motion between two objects. And that's what friction is. If we think about a box moving along the floor, and we were to try and give this box, or it's moving on a slightly wavy hill here, if this box has some kind of net force pulling it in some direction, friction is always going to oppose the relative motion. So the friction force is going to be opposing our net force. As I said, friction is a vector quantity, and it is always going to be parallel. It's going to be parallel to the two surfaces that are in contact. And as you can see from the diagram there, it's going to act in the direction that will opposes the slipping motion. Now we designated that as capital F sub F, which will be our force of friction, and that is directly proportional to the magnitude of the normal force. We talked a little bit about that, and we'll take a look at that, what that means in a second here. The normal force is actually the force that is pressing whatever two contacting surfaces we are referring to, or that are in question here, that are in play, and it's going to keep those two contacting surfaces together. Now the other day we had talked about if we just consider this block on a horizontal surface, the normal force is going to be equal in magnitude and opposite in direction to the weight of the object. So if we consider that same box, we have a force here, F sub g, or force due to gravity, which is the weight of the object. The normal force is going to be equal in magnitude, opposite in direction to the object's weight. And remember, our force due to gravity here is object's mass times acceleration due to gravity, or a gravitational field strength. Now to figure out the force of friction, we can use the following equation, where the force of friction is equal to our coefficient of friction times the normal force. And again, the normal force equal in magnitude, opposite in direction to the weight on a horizontal surface. So the constant here, the mu, is the coefficient of friction, which if we rearrange this, it is actually the ratio of the frictional force to the normal force, and therefore, since it is a coefficient, it has no unit. So if we rearrange this equation here, we'd get the ratio of the friction force over the normal force, and that's going to be our coefficient. And by kind of analyzing this equation here, we can see that, let's just say frictional force. The frictional force depends only on the object's weight. not going to matter how fast the object's moving. It's also not going to matter the area in contact. So if we think of a block, two blocks of equal size, one standing on end and one laying on its side here. If these are being pulled in the same direction, the frictional force of force 1 would equal the frictional force of force 2. So it's not going to matter how this block is laying, because what is constant between these two blocks is its force due to gravity, or its weight. And that's what's going to keep this frictional force the same. So we're really concerned about the weight here when dealing with friction. And we saw from our lab that we're going to be dealing with two different types. At least we'll talk about two different types today. Static friction, meaning when something is at rest, is going to be the force that opposes the start of motion. So it's the force that's in play before an object actually gets moving. So while the object is at rest, and we can apply a force to something and have it not move, we have to apply a greater force in order to overcome that static friction. Now once we get the object in motion, kinetic friction takes over. And kinetic friction is the friction between objects that are in contact when they're moving or when they're in motion. So before we start getting the block in motion, we're trying to overcome static friction while the object is at rest. Once it's moving, we are applying a force to keep the object moving, to try and offset the force opposing our motion, which is kinetic friction. Now in the lab that we did, looking at friction there, you should have seen from the cart that once the motion starts, the kinetic friction actually decreases, and we could continue to move that cart at a constant speed with less force once we overcame that static friction. And when we did that, that graph that we saw here, this had time, we had force here. What we saw, as we applied more force, we kind of saw this steep climb, and then once the cart got moving, the force became less. Extend this down here. And then it dropped off once we stopped pulling the cart. So what this graph showed is that the force of kinetic friction for two surfaces that are in contact, so the cart going down the track there, is going to be less than the force of the static friction for the same two surfaces. So the coefficient of kinetic friction is also going to be less than the coefficient of static friction. So kind of looking at these graphs here, and this is more of a perfect scenario example, you would have been able to fit this similar line to the data that you would have collected. So we basically have the force of static friction in the first part of our graph there, and where the motions, or where our graph dropped off here, this is where motion started. And then after that, we have a kinetic friction force that we're trying to overcome. So we can see the drop off there. Once the cart started to move, we overcame that static friction, we could then apply a smaller force to keep that cart moving at a constant speed. This kind of shows that the kinetic friction force is going to be smaller than the static friction force. Now we can determine coefficient of friction, not fraction. I'll have to fix that. From graphs. And we'll look at a graph here of the friction force against the normal force. Now, a graph of frictional force versus normal force or versus weight for a wooden block in contact with a wooden surface is a straight line for both static friction and kinetic friction. The coefficient is not going to change. It should remain the same as long as the two surfaces in contact are going to remain the same. Now, if we were to look at these coefficients for that wooden block, we should get two different lines. The steeper curve would be our static friction coefficient, and the more shallower curve would be our kinetic friction coefficient. Now we can figure these out because the coefficient of friction is equal to the friction force over the normal force, which is equal to the change in y over the change in x. So really what this is here, the slope equals our coefficient. So the slopes of the lines are the coefficients of static friction and the coefficient of kinetic friction. I'll leave you guys a little joke for today. Which books are the hardest to force yourself to read through? Friction books. Have a great day, guys.